Hello my dear students, welcome back to the IMS GATE Academy. Let's continue the foundation series on computer organization architecture. In this session, another topic from the memory organization, that is cache memory. So in the previous couple of sessions, like from memory organization, we have seen the specially memory hierarchy we have seen, followed by main memory. The main memory also happened in two sessions, like those you have not attended, you can go and watch the memory hierarchy we have taken, followed by main memory. So in the main memory physical structure and also like memory expansion, this thing we have discussed. So in this session, let's discussion on cache memory. What is this cache memory? So I given a brief introduction previous session, but let's see the cache memory design. Look, the cache memory, like I discussed the main memory. Is the cache memory, like if you look at the main memory or primary memories, okay, main memory or primary memory components, main memory or so primary memory. So primary memory components, if you see, we know the RAM, random access memory, and ROM, right? ROM. So read only memory we have. The RAM is again classified into DRAM, right? DRAM. So dynamic RAM, static RAM, SRAM, SRAM. Okay, dynamic RAM, SRAM. So these SRAMs are used to construct the cache memory. SRAMs are used to construct the cache memory. Getting my point? The SRAM, static RAM. So I have discussed in the previous session the static RAM nature. So we use the DRAM, so dynamic RAMs, for the main memory construction. The differentiation also which we discussed. Now we'll work out the importance of the cache memory and this design also. Importance of the cache memory is the design. What is this cache memory? The few points I mentioned here. The cache is the smallest, the fastest memory component among the memory system. The memory component, please understand, because you may confuse the register. Register is the storage element part of the processor. When I consider the memory components like main memory, cache, and secondary memory, among three in the memory hierarchy, this cache memory is the fastest and the smallest component. The purpose, please understand, purpose of the cache memory to use. I discussed also, like I discussed one point, 90% to 10% rule. From the empirical observation of the 90% to 10% rule, the introduction of the cache memory came into picture. And the cache memory, which is used to holding what? Frequently referred materials of the processor. That means frequently referred program instructions or data. So if it is referred several times, means it is going to reduces the average access time. So I mentioned, see, it is tightly coupled with the processor and usually contained on the same integrated circuit. Getting my point, all of you. So cache memory, the most of the system, the cache is part of the processor or CPU chip only. But in contemporary computer architectures, if we see, so one level of cache memory will be outside the processor, that we call level 3 cache memory. The cache memory can be level 1, level 2, level 3. Level 1, level 2 are part of the chip. When you have multi-core systems, each core having a local cache L1, and the L2 is a common to the all the processor, which is part of the like the same integrated circuit. Level 3 would be the outside. This some of the architectures you can visualize. But generalization, what I am trying to say, cache is part of the what? Chip, the processor chip only. The fundamental idea of the cache organization is that keep the most frequently accessed instructions and data in the fast cache memory. This purpose, what is the advantage? Memory access time, the average memory access time will be approach to the access time of the cache. It is just approaching to the access time of the cache memory. So that is the advantage of the cache memory. Understand? The presence of the cache memory, like you can visualize, but this is the part of the CPU only, see, part of the CPU only, okay. Some modern architectures have the one of the level, this the cache can be a level 1 cache, it can be level 2 cache, it can be level 3 level of cache will be there. So these two L1, L2 are part of the processor only, part of the processor. So L3 will be the level 3 cache will be the outside the processor. Outside of the processor, the processor means CPU. processor. Okay, getting my point, all of you. Now please understand, this cache memory maintains two things. Please understand, the cache memory maintains the locality of reference here. It maintains the locality of reference. Yes, Amit Goel, very good evening. Good evening, good evening, good evening. Yeah. So please understand the importance of the today's session. This session, we are going to discuss the cache memory, which part of the memory organization. The previous 2-3 sessions we had a discussion memory hierarchy followed by main memory, their physical structure and memory expansion, those things I discussed. Now let's focus on the cache, its implementation. From GATE exam point of view, we can expect 2 marks or 3 marks from this area, which is very important. That is the reason first initially we will understand the basics of the cache, then we will see the design part like cache addressing approaches, various things. Yeah. So any moment if you have a doubts, definitely just let me know so that we can address your doubts also. So what I was trying to say, cache memory is maintaining the locality of reference. What is the locality of reference? It is confined to some particular locality of a program. Program is contained two things, locality, non-locality. Means what? Locality, if I say some set of program instruction data are accessed by the CPU several times. Are you getting my point? Some program instructions and data which are accessed by the processor frequently, repeatedly accessed by the processor. We say these programs are confined to this particular location. Some part of the program code or instruction, or that program code nothing instruction data which may be accessed by the processor infrequently, which is not repeated, hardly one time, that we call non-locality of a program. So cache is maintaining this one, because the major objective, see, the instruction data which is repeatedly several times, those things if you keep into cache memory, always most of the time it will be right. If the processor is referring the same instruction again and again, so if it is present in the cache, it will be means reduces that access time, not required to go to main memory. So this is the advantage, which we wanted to achieve from the cache memory. Clear? So I said, locality of reference means in short interval of time, the address generated by the processor program refer to few localized area of the memory repeatedly accessed. Please understand. While the remainder of the program or remainder of the memory is accessed relatively infrequently. This point I want to conclude. Fine. This locality of reference can be of two types. The locality of reference can be two types. One is temporal locality, otherwise second with a spatial locality. Temporal locality with respect to the time, please understand. At particular time, or you understand, the particular information is accessed by the processor several times. Same information referred by several times. The spatial, nothing but please understand, address space, please understand. The spatial locality is address space. Address space means this particular address space is going to be repeated or accessed. So let's look at this temporal locality. Recently executed instruction is likely to be executed again very soon. Let's take, suppose if I take this is information is there. Please understand, this is item is referred by the processor, this is referred by the CPU. Okay. So now please understand, there is chances like this item is repeatedly accessed by the processor. Okay. So that's what I mean, right now. Recently executed instruction is likely to be referred by the processor very soon. So that is suggesting that temporal locality suggests that whenever a information item, that is instruction or data, is first needed, this item should be brought into cache memory because it is likely to be needed again soon. Are you getting my point? Particular information so need to be kept into cache memory so that it can be accessed by the processor in the future. That's one item it is talking about, is a temporal locality. So what is a spatial locality? Suppose one information that is, so just like a loop, just like a for loop. Yes, in a for loop also particular instruction. Let's take particular instruction. Example, x equal to x plus I doing. X is integer. When I is repeat, x need to be accessed every time. Yes, right, that is right. The spatial locality comes under, suppose, please understand, array element is there, array contains 100 elements are there. The first item you referred when the index 0. So, processor is likely to be referred index 1, index 2, index 3, yes or no? Now, this suggests, please understand, this suggests instead of fetching only one item from the main memory to the cache memory, it is useful to fetch several items, more than one items that are located adjacent addresses only, so that this will reduce as the future penalty. The spatial locality suggesting instead of fetching only particular referred item, just adjacent addresses also just keep into higher level memory. Higher level memory means cache. If the cache is divided in multiple levels, so keep it higher level memory, more data, more adjacent data. So in the future, processor may going to be referred the consecutive data. If it is referred, now what happened? You are going to reduce the future penalty. Means this future penalty means it is does not require to access main memory again, because it is available there. The special example I given, array, accessing the array elements comes under what? Spatial locality. I hope it is clear. Yeah, I hope it is clear the point. The cache is maintaining two things, either this can be happen, this can be happen. Yes, if the spatial locality working more, you understand the iteration of the cache is more, overall throughput of the system also high. This point we can observe it. Any more doubt? Any more doubt? Okay. So now the basic idea we got in a cache, the cache. The spatial is for the data. Yes, spatial is for the data. Please, it is data. The spatial example I given, right? Array, accessing the array elements. So set of words are there, like no array having exactly. Temporal is for instruction. Exactly, you are right. Instruction, same instruction, repeated access. Or you understand that temporal can be a data. Example, I'll tell you, no. For I equal to 0, you written x equal to x plus I, you written something. Okay, x equal to x plus I. So x is you are repeating several times, right? Same one element you are accessing many times till that loop completes. When I equal to 0, when x is referred, we can predict the x will be referred again. So that x can be keep into cache memory, so that till this loop completes, x can be accessed by the cache memory, not by the main memory. This is concerned for one item. It can be one item of the instruction, it can be one item of the data. The spatial is most concerned as for data which you mentioned, because when you access a more data, consecutive data. It is clear? I hope it is clear. Now let's move on to the design part of the cache memory. Yeah, design part of the cache memory. So design part of the cache memory means, the first of all, designing means what? So cache is present in the hierarchy, right? How information is kept in a cache memory? How information moves from main memory to cache memory? How information moves from cache memory to processor? So these aspects which we are going to study. So that's what design part of the cache memory can say. What are the elements which involve the cache design, which I mentioned? First of all, we must know the memory organization of the cache. So memory organization, nothing but here you have to understand organization of the cache as well as the main memory. Organization of the cache as well as the main memory organization. So this aspects you might have covered from even operating system point of view also. The here cache point of view observe it. So address mapping techniques that need to be studied. What the address mapping techniques? So how we are going to convert address space from the cache memory to main memory? Address mapping from cache memory to main memory. There are various address mapping methods, the first approach is direct address mapping. The second approach is associative address mapping, also known to be full associative. The third one is a set associative address mapping, associate mapping. There are three approaches are there which will map the cache address to main memory address to cache memory. Fine. So block replacement strategy, this aim of discussing this block replacement strategy to move the reduces the number of moves. Reduces the number of moves to understand. So when you are mapping the blocks of main memory into cache memory, need to be reduce the number of misses. It is kind of like you might have studied from operating system point of view page replacement algorithm. Am I right? Page replacement algorithm you might have studied, means whenever main memory frames are full, now process want to load a page of a process from secondary memory to main memory, for which no empty frame is available. Now operating system has to run some decision policy to select one page from out of frames, remove them and allocate another one. So what order, what kind of policy you are applying for selecting a page for removal is completely depends on the replacement algorithm, page replacement algorithm. The similar situation occurs for the cache memory. So we have to discuss the page replacement algorithm, but here block replacement algorithm. Examples I can say the first in first out, LRU, MRU, optimal algorithm like this. Finally we will see the cache updating techniques. So cache memory has some limitation, please understand. It suffers from the cache coherence. Coherence means data inconsistency problem is there. Data inconsistency means, please understand, in the memory hierarchy, same information is available differently at different levels of the memory hierarchy. So that leading to inconsistency means all the level information should be same, correct or not? See, whatever information consists in a cache memory should be there in main memory, so that should be there in secondary memory, right? Because some copy of the secondary memory we move to main memory, some copy of the main memory we move to cache memory. So all the information should be same. Inconsistency means all the levels may have different data, same item should be there differently having. So that having inconsistency. So this inconsistent problem can be resolved. Proper updation techniques. Updation techniques are, so you might have studied write through updation. Second is a write back. So write back updation. Two protocols are there. So these two protocols works like multi-programming, like single CPU cases. If multi-processor case, these two protocol may not sufficient. Other protocol need to be studied. For since we focusing the single processor, single CPU architecture, so these two protocols I am going to be cover. So this is a rough idea I am giving what I am going to discuss on memory design, the cache memory design. Okay. The first initially we will spend some time to understand organization of the cache memory and organization of the main memory. So shall I move on to the first one. What is the first one? Memory organization. Memory organization. So what is the memory organization here? Two things need to be understand. Cache memory organization, main memory organization. Okay. So main memory organization, please understand, main memory organization. What is this organization? Arranging this cache memory into blocks means arrangement of cache memory in terms of blocks, okay. So this also arrangement of main memory in terms of blocks. So arrange them in terms of blocks. That is what organization here. Let's understand with the example betterly. So first of all, if I consider for main memory, suppose main memory, if I consider the main memory, okay, main memory, okay. So in the last previous two sessions, I have discussed very clearly word addressable memory, byte addressable memory, means internal organization of the memory we have seen, internal structure of the main memory we have seen, like word addressable. The words nothing but collection of cells. Words nothing but collection. How to address them, how to calculate the size of the main memory, those things which we observed in the previous session you must watch, because that is the basic thing which I covered. And also we have understand the endians. So big endian, little endian concepts we have done. How to order, order of storage of the data in a memory component. Order of storage. Either you can store little endian or big endian. Those differentiation also we have discussed. So I hope you understand that thing. So now directly we can take up what? Block arrangements only. Directly we can take up the block arrangement. So let me take, please all of you, main memory. So main memory I am taking the 128 bytes. So 128 bytes. This 128 bytes memory, I want to organize them into 16 blocks size. So 16 blocks, 16 words. Okay, I am taking the block size as, so block size. So block size is considered 16 bytes is there. 16 bytes is there. Please understand. Okay, 16 bytes. Here organization, please understand, arranging the memory in terms of blocks. Arranging the memory in terms of block, either main memory or cache memory, because address mapping means, please understand, we have to convert the what cache address, so the memory address into the physical memory address or physical address into cache address. So now the unit should be same, main memory cache memory unit should be same. How it will happen, we'll see. 128 bytes main memory I am taking, and block size is 16 bytes. Okay. How many blocks will get? How many blocks? Number of blocks. So number of blocks, just I am indicating as a n, okay, equal to, so total size of the main memory 128 byte divided by 16 byte. So this we can express 2 power 7 byte by 2 power of 4 bytes, right? 2 power of 4. This is 2 power of 3. 3 means 8 blocks will get. 8 blocks will get. Okay. 8 blocks will get. Look this. So before organization of this memory, before organization, how main memory looks, please observe. So this is the main memory, okay. This main memory, okay. What is size of the main memory? 128 bytes are there, right? So like location wise, if you see, this is the word byte number, okay, byte number, okay. Okay. How many bytes are there? 0, 1, 2, 3, 4. So 127 bytes are there. I hope you understand. We know the internal structure also shown, like this is 128 by 8. So here is data. What is the data bus size? So data bus size 8-bit, right? Data bus size 8-bit. So how many bits required to address this memory? Yes, somebody tell me. How many bits required to address this memory? Yes, Amit Goel, can you please tell me how many bits required to address this memory? If the memory size is 128 bytes, how many bits required to address them? So 128 means 7 bits required or not? 7 bits required. With this 7 bits combination, I can identify one of the location. So this is before organization of this memory component in terms of blocks. Now look at the, let's mark it, this is A, this is A. Look at B. B means what? What is B? B is after this memory organization in terms of blocks, Look all of you. Look all of you. This is the main memory. Size is how much? 128 byte. Okay. 128 byte. What is the block size I have taken? 16 bytes. Look this now. So I am dividing block number 1, like block number 2, block number 3, like this. How many blocks I will get it? So now indexing from 0, 1, 2, 3. So 15, total 16, sorry, 8 blocks you get it, right? So this is 7. Total 8 blocks means 7, 0 to 7, right? 0 to 7. What is size of the block? Size of the block 16 bytes are there, right? Size of the block is 16 bytes is there, right? Like bytes 0 to 7, so 0 to 15 bytes. So 0 to 15 bytes will be there. Total 128 bytes are organized in terms of blocks. Is it clear? Any doubt here? Any doubt? The total 8 blocks are which are number from 0 to 7. 0 to 7 you can see block size 16 bytes is. This is the after organization. Now see, address bits, how many bits required? 7. For this, here also address bits 7 only. How to access here? Address bits here also 7 only. Address bits are 7. Address bits are 7. But we divided into blocks, right? Like we have divided into blocks. So any data you want to access in a memory, so that should go with a block number. So first of all, you have to access the block number. Then data we have to, within a block you have to access the data. So we call offset. This we call block offset. We call offset. How many blocks are there? how many 8 blocks are there? That means you understand 3 bits required for this. 3 bits required. Okay. So within one block, how many bytes are there? How many bytes are there? 16 bytes, nothing but 4 bits required. Understand? See, now 7 bits of address, it was only single address was there. With this we can access. Now we made into blocks. First of all, leftmost, please understand. So when address 7 bits is there, like MSB of 3 bits, 3 bits identify the block number. This will identify the block number. Which block number? If all 3 bits are 0, block number 0. If all 3 bits are 1, block number 7. Correct. So now leftmost, rightmost, we are calling rightmost least significant bits of 4 indicates. So data within a block, data within a block. I hope you understand. If all 4 bits are 0, you are accessing the first byte on that particular block. I hope you understand. Because since the memory is divided into blocks, in order to access any data in the memory, you have to identify first block number. Once you get the block number, within a block number you can get the access the data of a block. I hope you understand this point. Any doubt here? Any doubt when I consider the main memory? So let me take another example, so we'll get a clarity. So example 2. Suppose if I take 1024 by 16, okay, 16 bits RAM is there. 16 bit RAM, the main memory is there. 1024 by 16 bits is there. Now see the A, before organization. Let me take again. So block size. Block size is 64 words are there, assume that. Block size is 64 words are there. Now tell me how many blocks will get? Number of blocks. Suppose if I indicate n, number of blocks in this case, if I indicate n. Now what is size of the size? Size is what? Memory size 1024 into 16 bits are there. 16 bits divided by 64 words are there. One word is nothing but 16 bit only. One word is nothing but 16 bit. This will cancel. How much? This 2 power of 10 by 2 power of 6. So this is 2 power of 4. This gives the 16 blocks will give. It is giving how many? 16 blocks. I hope you understand. So first one you see, before this organization, before making memory in terms of blocks, before organization. Before organization, if you see how memory looks. Okay, this is the memory. Okay. What is size of the memory? 1024 by 16 bits, right? 16 bits. Understand? See. So this word length is there. What is word length? Word length is 16 bits. Okay. The 16 bits are there, right? 16 bits are there. 16 bits nothing but 2 byte only. 0, this 1, this is 2, this is 3, like this, 1023 is there. Now here data bus size. What is data bus size? Data bus is 16 bits only. Address bus, address pins are address bits required for this one. 1024 word addressable memory, 10 bits required. So 10 bits required to address them. So now I did not made this memory in terms of blocks, still its words form only there. So now B meaning what? After organization of this memory in terms of blocks. So now see the memory. This is the main memory. Okay, this is the main memory. Now you have to make it divide into blocks. Block number 0, block number 1, block number 2. So like this, total number of blocks, how many you got? 16. So block number 0, block number 1, block number 2, block number 3, like this, block number 15. So what is size of the block? Size of the block is how many? 64 words will be there. 64 words will be there. I hope you understand. 64 words will be there. So this block number 0, please observe the block number 0. Word number 0, 1, 2, 3, 63 will be there. So from this start from where? 64, right? 64 to 127. This start from 128 to like this, you know. So last will be 1023 will be there. Because total will be 1024, right? So now 1024 words are arranged in terms of blocks. The block ranges you see. The block range you see 0 to 63, 64 to 127, 128 to this one. Correct or not? I hope you understand. Now address if I want to access. How to access the memory? How to access the memory? How to access the memory? If it is block wise. Now address bits. Address bits, how many are there? 10 bits are there, right? 10 bits are there, right? Yes or no? This need to be split into two parts, right? What is the first? Leftmost bits gives the block number. So next this will give the word number or byte number. You can simply say offset. Offset you can say. How many blocks are there here? 16 means what? 4 bits required for this. 4 bits. So this bit 6 bits required. Yes or no? Hi Nikhil Gaur. Look at here. So block number 4 bits. This block number 4 bits gives the block number in main memory, right? In main memory. So this 6 bits gives a word number within a block, within a selected block. Please understand this point. Okay. So this is like you see now here. Here is address bits of 10. Okay. So out of 10, leftmost 4 bits take. With this leftmost 4 bits, you can identify one block out of 16. Once you get, so within particular block, you can get a word number by using the rightmost 6 bits. So that give word number. I hope you understand the arrangement of a memory in terms of blocks. This we call memory organization in terms of blocks. I hope it is clear, because so this is the basic thing we require to understand the cache design, means cache mapping methods, cache address mapping methods. I hope it is clear. Suppose if I ask one question here, all of you, please, if I ask you question. Now this memory only. What is the memory? So this is a memory only taken 1024. Second example, 16 bits is there, right? Yes, sir. This the memory is there. Okay. We made into blocks, right? We made into blocks. What is the block size I have taken? Block size is 64 words I have taken. Okay. Word addressable memory, 64 words are there. Okay. If I ask you question, the range, block range, the word range in the block, suppose if I ask you word range in the block, let us understand how we can go and answer. Here I am writing the block number, okay, block number, decimal. Here is word range, okay, word range, let us observe, word range, block number. Okay, so I am asking this particular data only. I am considering. So few things we can observe here. So total how many blocks are there in main memory? Can you answer? How many blocks are there? All of you. How many blocks are there? With an example I consider 16 blocks are there. Block number 0. What are the word range? Means the block size is 64 words. Word range is 0 to 63, right? 0 to 63. Correct or not? Say yes or no? Suppose if I take block number 1, what is the block number 1 as? Block number start from 64 onwards. 64 to next is what? 127. Correct. Now block number 2. Tell me. Block number 2. 128 to so 128 plus 63. How much this value? So this is 1. So this is 90. 9, right? So 191. This is 191. Similarly, block number 3 as 192 to 200 and so check it again, 192, 63 we add it. This is 5. Added this 10. So 255. Right. Similarly, if I ask you question Okay. So total how many blocks are there? Total how many blocks are there? Total blocks are 16. 16 blocks. If I ask you 12th block, what is the range? 12th block range. What should I do? 12, in order to find out the 12th block range, what should I do? So 12th block, right? 12th block into, okay, its size. What is block size? 16. 16. Block size 16. 12 into 16. 2. This starting will get next. Next will give this 12 into 16. So plus 15 extra you have to add it. So that is the range will come. Here you see now 0. Block number 0 into 16. 0 will got. 2. Block number 0 into 16. 0 plus 15. So 63. Sorry, this is not. Sorry, it is not 16 ma, because block size I have to take it, right? Sorry, this 12 into 12th block, right? What is block size? 64. 2. 12 into 64 plus 63 you have to add it. This is the range it will give. I hope you understand. So this this value you can calculate like this 640 plus 128. This is 8. This is 6. So 767. This gives a 12th block range. 768 is the starting one. 2. The 63 if you add it, this is 1. So this 12, 13. So 831. 831 is the range it will give. So 831 is the range it is giving. I hope you understand. Similarly, if I ask you last block number 15. So block number 15 is what is the last range? 1023 only, right? You subtract 1023 minus 63 you have to subtract 0. This is 6. This is 9. 960. 960 only. 960 plus. So 63 will be same only, right? 1023 only. Correct. This is correct. This is the last block value. Last block words are there. 962 1023. This is last block task. So now I want to make you generalization. What is the generalization, sir? What is the generalization? Suppose any block number, let's take in here I am writing, no? Here it will go, right? Any block number, let's say P is there. Any block number P, whose range how to get it? So now range I am writing, no? P, block number P into size you have to take it. Size of the block you have to take it. Let's say size of the block is N. This starting will be like this. Next what? P into N, okay, plus N minus 1 is the range, please understand, okay. This is the range it will give, okay. So now I am writing generalization. Pth block, okay. So Pth block has the word range, okay, word range from where? P into N, okay. So P into N2, okay. P into N plus N minus 1 is the range. Where? What is the N? N is a block size. So block size in terms of words or bytes. So this is the range, because this will help you. No, please understand. In numerical problem solving, this will help you in case of numerical problem solving. Are you getting my point? I hope it is clear. So wherever memory is organized in terms of blocks, if they ask word range in that block, simply you see the block number, you have to multiply the size of the block, you will get the starting address, starting word number or starting byte number of the block you will get. Add size minus 1 to that. So like N minus 1, that will give the end range. I hope it is clear. So you mark it this one. So this is the example 0th block. Like you can check for the formula, will it work out or not. Suppose now block number 1, if I take P, block number 1, P is 1. 1 into size of the block is 64. 1 into 64, 64. 2, 1 into 64, right? 64 plus 64 minus 1, 63. So what is the value? 127. This is working, right? Yes. This is I want to say. Chalo ma. Next. So the same thing will happen for cache memory also. So now see, Memory organization, what I said, you organize the blocks wise, organize the cache memory, main memory into block wise only. So, main memory example I given, similar thing will go for cache memory also. Take the cache memory, take the block number, block size, divide into blocks, arrange them into block wise, access goes again in terms of block number and offset only. I hope you understand the point, this thing, fine. So, now see the cache address mapping techniques we will observe. So, now we will observe the second one is what? Cache address mapping techniques. The cache address mapping techniques. Cache address mapping, address mappings. Cache address mapping we will see. Cache address mapping we will observe now. Look all of you. So, this cache address mapping, please understand, cache address mapping methods, converts the main memory address, that is a physical address into cache address. CM is cache address. Physical address into cache address, it will convert. So, you see the memory hierarchy. This is a memory hierarchy which we discussed, right? Memory hierarchy. Okay, memory hierarchy. So, bottom level memory is what? Magnetic disk. Bottom level memory is magnetic disk. Top level memory is what? Cache memory. In middle, what? Main memory. Please understand. So, this level 0, level 1, level 2, 3 level memory hierarchy if I consider. So, bottommost level is the magnetic disk, the top level is what? Cache memory. Now, main memory is occupied the central position, right. Now, see, data will move from disk to main memory, right, by the operating system in terms of pages or segment wise. So, data will move in terms of pages or segments from secondary memory to main memory by the operating system. The page size would be in terms of 4 KB, even 4 MB also, 4 KB to 4 MB. But initially original day, like old days, the page size would 512 bytes to 4 KB. Now, in the modern architecture, page size have improvised in terms of in MB also. Now, see, main memory to cache memory, please understand. Main memory to cache memory, data will move in terms of blocks, please understand. Data will move from main memory to cache memory in terms of blocks. So, this is done by the hardware, that is cache controller. Cache controller will take the responsibility of transferring the data from main memory to cache memory. Now, see, main memory size is different, cache memory size is different, right. Main memory size is different, cache memory size is different. Now, understand, cache address mapping converts this main memory address, please understand, this main memory address into cache address. Main memory address into cache address, please, that we call physical address into cache address we need to convert. So, there are several approaches for converting the logical, main memory address, physical address into cache address. One is direct address mapping. One is direct address mapping. Second one is what? Associative address mapping. Associative address mapping. Second one is associative address mapping. Third one is a set associative address mapping. Getting this associative address mapping also known to be full associative address mapping. We can say either associative mapping or full associative mapping. The third one is what is the third one? Set associative mapping. So, there are three mechanisms we have which convert the the main memory address into cache address. I hope you understand importance of the address here, address schemes, address mapping schemes. Now let's work out one by one. The first approach is what? Direct address mapping. So first approach is what? Direct address mapping. Direct, the first one I am taking, direct address mapping. Direct address mapping. Direct address mapping. Let us understand clearly how. This direct address mapping scheme, simplest method, please understand, simplest method to implement. Simplest method to implement. But the problem, please understand, it is a slow mechanism. Please understand, direct address mapping is slower mechanism. In terms of performance means here conflict penalties are more. Here conflict penalties are more. So in terms of performance, if you see, it is a poor performance, slower mechanism. So but simple to implement it. It has more conflict penalty. So let's work out, let's understand what this term says with the example in the further things. Okay. Now we will see the framework of the address mapping, cache address mapping, direct address mapping. The framework of the direct address mapping says, please understand, okay, what is saying, how you are going to map. If I use this direct address mapping, how you are going to map main memory into cache memory. Okay, please understand. The step number 1, please understand. There are 2 simple steps it will tell. Step number 1, okay. Step number, please understand. Divide the cache memory. Divide the cache memory, main memory. Okay, main memory. Divide the cache memory, main memory into equal sized blocks. Please understand. Are getting, divide the cache memory and main memory into equal sized blocks. So that's what memory organization I did. Main memory, cache memory you have to organize into blocks. Here how? Equal sized blocks you have to do. Both the memory you have to make it block was equal size. This step number 1. So step number 2, please. Step number 2. So now please understand. Map the main memory blocks. Because main memory we have arranged in terms of blocks, right? Map the main memory blocks into blocks of cache memory by using, okay, by using the function called, what is the function here? They said no, they said function called k modulo n. What does this meaning, please understand? What does k modulo n we have to use? What is this line says, we'll understand. Okay, that is like, no, here mapping how. I am just continuing the second line only. See, please understand all of you. That is kth block of main memory you have to map, right? Main memory blocks you have to map into cache memory, right? Kth block of main memory is mapped. Kth block of main memory is mapped to the k modulo n, nth position. So the position nothing but block number. K modulo nth block, it will be block number. Okay, k modulo nth block number. So you have to map kth block of main memory is mapped to this location, in this position. So what is a k here? K is what? Main memory block number. So main memory contains a set of blocks, assume that. Are you getting my point? So K, please understand, K is the main memory block number. So the block numbers are 0, block number 0 it could be block number 1, it could be block number 2, it could be block number 3. Like suppose if contain m blocks are there, m minus 1, I hope you understand. Here please understand, main memory, okay, main memory contains m blocks, assumption. Main memory contains m blocks. Now K is what? It could be 0 or 1, 2 up to till m minus 1. Clear? So what is n? N, please understand, n is what? Number of blocks. So number of blocks in cache memory. Cache memory. Okay. Here one thing you would understand, m is greater than n. M is greater than 1. Yes, obviously that main memory is larger size in cache comparison to cache memory. Main memory size is larger than cache memory. I hope this point is clear. Okay. There are only 2 points. What are the 2 points I am repeating? Understand clearly all of you. How mapping occurs from main memory to cache? Very simple. Organize the cache and main memory equal size blocks. Blocks of main memory map to cache memory block. That's it. How mapping happen? Use a function called k modulo n. In this algorithm, this mechanism. K modulo n is take any block number from main memory, apply to this function k modulo n. This gives the block number. In that block number, you place it. You cannot place that randomly. You have to use this function. Fine. So that need to be understand. Okay. So this line is clear. I hope this is clear. Now let's understand with example. Let's try to understand with example. Okay. Let's try to understand the example. Consider main memory. Okay. Main memory has 512 words. Main memory has 512 words. Cache memory size is 64 words. Okay. And so I am taking the block for dividing this two component block size. I am taking the block to divide this memory into blocks. Block size is 16 words. Word length is 16 bit. Word length is 16 bit. Assume it word addressable memory. Now understand, if you look at the cache memory, so if you look at the main memory, okay, look at the main memory, all of you. What is size of the cache memory? 64 words are there, right? You would arrange them in terms of blocks, number of blocks. So number of blocks, I am indicating capital N in cache memory. 64 words by what is the block size? 16 words. This will give 4. Understand? This is a cache memory, block number 0, 1, 2, 3, 4. So 0, 1, 2, 3, 4 is there. This is a cache memory. I hope you understand. Similarly, so number of blocks. I am taking m in main memory. Equal to what is the main memory size? 512 words are the very small example I have taken. By block size is almost 16 words are there. This is 2 power of 9 by 2 power of 4. This is 2 power of 5. 32 blocks will get. Main memory has how many? 32 blocks are there. Because I have taken this data to understand simple data, because large data you may confuse. Simple, there are 32 blocks main memory, 4 blocks in cache memory. How this mapping occurs, will observe. All of you. It is clear, right? Now see the scenario. Memory pattern. Now see the memory pattern here. So now see this main memory, okay. Otherwise, let me take Now look at the catch. So we divide into block wise, right? Yes or no? Block number 0. So block number 1. So block number 2. Okay. So like this, last block. How many blocks are there total in main memory? How many blocks are there in total in main memory? 32 blocks. Now look at the cache. 1, 2, 3. Fine. See the block number 0, block number 1, block number 2, block number 3, like this, no? 31 blocks are there. Total M equal to 32 blocks, right? This is what? Main memory. This is main memory. Size how much? 512 words are there. This is what? Cache memory. What is cache memory size? 64 words are there. So this is block number 0, right? Block number 0, block number 1, block number 2, block number 3, right? Yes or no? Block number 3. Total how many blocks are there? 4 are there, 4 are there. Now see, please carefully observe, all of you, how mapping goes, will observe clearly. Okay. Now what to do? So what a diagram is shown, the map, you have to map from main memory to cache memory. You have to move, somewhere processor will be there. So how mapping goes here? If I use what direct mapping, he said function called k modulo n, you have to use it, k modulo n, you have to use it. Understand what this says here, all of you. So we have block size 0 to 31 blocks are there. 0 to 31 blocks are there. Let's take, suppose if I want to map 5 modulo 4, fifth block of main memory I want to place into cache memory. Mapping nothing but take a block from main memory, place into, where to place? So you have to apply the function called k modulo n. 5 modulo 4 1. So now in a block number 1 5 you have to place it. That's meaning in block number 1 5 you have to place it. Suppose 10 is there, 10 modulo 4, 10 modulo 4 gives what? Reminder. Modulo operation giving what? Reminder. What is the reminder? 2. Where to place 2? In the block number 2 you have to place 10. Getting my point? Suppose block number 8, 8 modulo 4 0. So you have to place it here, 8 modulo. Suppose block number 15, 15 modulo 4, this gives what? 3. So 15 is placed. 15 is placed. Block number 20, 20 modulo 4 0. So 0th block you have to place, but 0th block already block is occupied. What to do? Remove the block number 8. If 20 is essential, remove the block number 8, place 20. If I say 25, 25 modulo 4, how much? 1. So 1 in 1 already is there, you remove 5, place 25. That will go. Suppose if I ask 0th block, where will map? So 0th block will map here. 1 will map here, 2 will be map here, 3 will be map here, 4 will be map here, 5 will be map, 6 here, 7 here, 8 here. See now round robin fashion. See the sequence number block, if you take 0 1 2 3 4 0 1 2 3 4, like the round robin fashion we are allocating modulo function going the round robin fashion. Correct or not? Now ask a question. At a time how many blocks can be present in cache memory? 4. Is it not? 4 only. Out of 32, 4 only will be there, right? It ratio is what? Maximum. So 4 blocks will be there. Now what are the blocks are referring to block? This is the block 0 map. In a cache memory, block 0, block 1, block 2, block 3. So I am asking all of you, please. For block number 0, what are the blocks are referring? What are the main memory blocks? I am repeating the question. What are the main memory blocks are referring to block number 0? That is block 0. Block 4 will be there, 4 modulo 4 0. Block 8 will be there, block 12 will be there, that's 16 will be there, right? 20 will be there, 24 will be there, 28 will be there. I hope and 1, 2, 3, 4, 5, 6, 7, 8. 8 blocks are mapping. Simply 32 by 4 is 8. 8 blocks will map to one of the location. Similarly, block number 1. For block number 1, for block number is 1, this is 5, this is 9, this is 13, then 17, yes, 17, 21, 25 and 29, right? Similarly for block number 2 is what? 2, first 2, 2 modulo 2, 2 modulo 4 is 2 only, 2, then 6, then 10, then 14, then 18, then 22, comma 26, comma 30. Similarly for block number 3, what are the main memory blocks will map? Yes, ma, quickly answer it. Quickly answer it. So that's 3 will be there, 7 will be there, 11 will be there, 15 will be there, 19, 20, 23, this is 27, 31. See, 0 to 31, right? 0 to 31, total 32 blocks are maps like this. 8 blocks map here, 8 blocks here, maps here, 8 blocks here. Out of 8, 1 will be there. Out of this only, right? Out of this 8, 1 will be there. Yes or no? Out of this 8, 1 will be there. Simple. So I hope you understand mapping. Simple. I am repeating the two statement. Divide cache memory into blocks. Block of main memory you have to place into cache memory by using function called k modulo n. K modulo n will give the location, the block number, block index it will give. In that block you have to place it. That's it. This is the what? Storage mechanism. But question please. How to access data? How to access the data from cache memory or main memory? That need to be understand. How to access is important. Getting all of you. How to access is important. So now let me show properly whenever reference comes from the processor, how to access this thing we need to understand. Fine. Now look this all of you. Now look this all of you. So process, let's say process PI who is running in a CPU, is running in a CPU. Okay. This processor who is running CPU, this program will generate address. Program will generate address. Please understand address. Address we call logical address. Address generated by the processor, logical address. Okay. So this logical address we converted into by using main memory unit. Main memory unit. So we are converting into physical address now. Physical address. Okay. Physical address. So this memory management unit can be a page table, it can be a segment table. Segment table, please understand. The address generated by the processor we call logical address. The logical address completely different than the main memory, means where my program instructions or data is present, need to be translated. Logical to physical need to be translated with help of page table. So these concepts you will be learning from operating system point of view. I hope you have studied from operating system point of view, that is a memory management. Now, so physical address to respect to whom? Main memory only, right? Main memory only. So now see, take the physical address, go to main memory. This physical address, please understand, generally we split in two things, page number and offset. They split and get the page number, get the data given to the processor. This will happen. If the cache memory is not there, if the cache memory is not there, now please understand, say case number 2, process PI who is running in a CPU, please understand, okay, generate the program generate the logical address to fetch instruction from the memory. So this logical address I am converting into physical address by using the hardware called memory management unit. So now we will be getting the physical address. Now please understand. Now here is a cache memory, please understand. Here is a cache memory, please understand, all of you, okay. Here is the main memory, here is the main memory, okay. Now cache memory we inserted. Now take the physical address, do not go directly main memory, go to cache memory, please understand, go to cache memory, okay. You have to go to cache memory, search in cache memory. If it is presented, take the data, hand over to the processor. If it is miss in a cache memory, then obviously you have to go to, please understand. Two cases will happen, please. Whenever reference comes here, okay, address, physical address, how cache is organized? How cache is organized here? Cache is organized block wise only, right? Blocks wise only, right? Blocks wise. So far we have seen block wise. So now to what to do? This physical address, please understand, this is the basic information mark. You have to divide it into two parts. I shown block number and offset. So block number offset, okay, offset, okay. Take the block number, search into cache memory, okay. If that block is presented, okay, take the offset bit, search a word within a block and hand out to the processor, that's fine. Case number 2, please understand. So I am trying to search, here is a cache miss, that is not there. Then what to do? take this physical address as it is, go to main memory, please understand, go to main memory. So this physical address need to be divided. Again block number, we call block number, page number same only ma, offset, page block same only. Take the block number, search into main memory, search into memory, like you see, search into main memory. You will get the required block compulsory. Now that block you have to map, please understand, here is a mapping function will occur. If you are using the direct address mapping, then see k modulo n, you have to substitute. So you take the physical address, divide into block number offset, the block number you will get a block, right? That block number apply k modulo n. So that gives some address, see now, k modulo n, one block you got k modulo n, that give address. In that cache you update, place the block, restart the instruction means again it has to generate the address. When you regenerate the address, that logical address will translate into physical address. The physical address will search into cache memory by splitting block number offset. With this block number, you get the block because you updated now. You will get a block number. So you will get concerned block you will get. So within a block, read the data, hand over to the processor. So this will happen. Even third case I am telling you, if main memory miss is occurred, if main memory also page fault occur, obviously you have to go to secondary memory, concerned page you have to load into main memory, update. So that block you have to bring into main memory, update and restart the instruction. This will happen. I hope you understand the searching. But let us see how exactly searching happens for cache. How searching happens for cache. Okay. So now I'll ask one question. What is the main memory size? Now see, please, one more important point you need to notice. Whenever a process is generate the address, processor really, please understand, do not have any idea or do not have any knowledge of presence of the cache memory. Please understand. Presence of the cache memory is not knowing to the processor CPU. So now please understand, processor always generate the address which is to main memory only, to access into main memory only. But middle we kept the main cache memory, will read that address, physical address, will read, split into, will try to search in cache only. To speed up this memory operation, some memory component we place, it is not known to the processor. It is thinking that I got a data from main memory only, because since it generated address to main memory only, he is thinking that I got a data from main memory only, not from the cache. If cache is presented, he will feel happy because within a time you will get a data. Getting my point? Now look at here, this example. What is main memory size? How much? Answer everybody. What is size of the main memory? 512 bytes. What is the address for this? How many address bits required? How many address bits required? 9 bits required, right? Yes or no? Now look at the here. Process PA who is running in a CPU, okay? This process PA address space is what? 512 bytes, assume that. Process PA address space 512 bytes. Now please, logical address something is there, it generated. Now this logical address we convert into physical address, okay? Physical address of how many bits? 9 bits, okay? By using what? Memory management unit, we converted logical address to physical address, we convert 9 bits address we got. What I told you, if cache is not present, I will go to main memory directly, yes or no? If cache is not present, I will go to main memory. So this 9 bits, we have to split into two things, block number and offset, right? Offset, okay. Here is how many blocks are there in main memory? This example only. 32 blocks are there, right? So 32 nothing but 5 bits required for this. Block size is 16 words means 4 bits required. So with this I can access. But now cache is present, right? Case number 2, process PA who is running in a CPU, want to fetch a data, generate the logical address. This logical address is converted into physical address of 9 bits we converted, 9 bits we converted. Here is no cache consideration, no cache memory, okay? Now cache is presented by using memory management unit, okay? Now this 9-bit address you have to take, search into cache memory, please understand. So if miss occur, then only you have to go to main memory. If miss occur, we have to go to main memory. Clear, all of you? Now how to search 9-bit address, please understand. Now physical address is 9 bits. So 9 bits we have to divide into block number and offset only, right? Yes or no? Block number, offset. Now cache, we want to search into cache memory. Please understand carefully, everybody. Cache memory, we have to search. How we arrange the cache memory? See the example. Cache also we organize blocks only, right? Blocks only. Now look at here. How many blocks are the cache memory in that example? This example I am considering. How many blocks are there? 4 blocks are there. So 2 bits required for this, right? Yes or no? So now 9 bits, 2 bits, plus 7 bits required to offset. It's saying like this. But how many words are there in a block? 4 only, right? So 4 only. So 16 words are there, nothing but 4 bits only required. Yes or no? 4 bits only required or not? Because block, whether it is in main memory or cache memory, size will not change, because the block which comes from main memory to cache memory came, size will not change, since for 16 bytes only 4 bits required. So now since cache memory has 4 blocks, 2 bits required, with this 2 bits combination 0 0 0 1 1 0, we can write it. Let's take some address comes, 2 bits comes. Okay, now we will search. Look this here. That take the 2 bits combination like 0 0, right, and 0 1 1 0 1 1. Please understand. So now see here I am writing 2 bits combination, any 0 0 something comes. Suppose 0 1 comes, assume that 0 1 some 4 bits came, but 9 bit address, suppose assume only this only required, right? With the 2 bits I will search the block number. Let's say block number 0 1. Fifth block is there here. Yes, block is there. One challenge will come here, please understand. One challenge will come. I have taken a block number of bits, 2 bits. I search the block number in cache memory. Let's say 0 1. There is a block 5. The question comes: does block number 5 is belongs to me or somebody else? That we don't know. How, sir? How, sir? So block number 1 5 is there. So because this block position, the block number 1 position, 8 block can map. Yes or no? See, 5 can be there, 1 can, 9 can, 13 can, 17 can, 21, 25. Any one of the block can present. But how to know the presented block belongs to you or not? Simply I got a block number address, I search it saying that block is there. But how we are guarantee that block belongs to you? So that information is missing. Hence, so this 2 bits combination block number is not sufficient. Some more information required to search. Now please understand, I am concluding. Physical address, please understand all of you. Physical address under direct mapping is divided into 3 parts now. The physical address in direct address mapping, to search the block number within a cache. So this address is divided into 3 parts. Please understand. Rightmost one we call word offset. In the middle one is we call block offset. The last one is the tag bits will say. We will understand the meaning here. Meaning we will understand. Now physical address, how much was there? Physical address is 9 bits, right? Now please understand, this word offset W means word offset gives, okay, gives word number, okay, word number, right? All of word number within a block, please understand, within a block, word number within a block. Now number of bits required for this field, depends on the block size. So I am concluding. Now word offset depends on log of block size. This need to be understand. Generalization I did. Block offset nothing but giving the word number within a block. So word number, the number of bits required for this field depends on the block size. In our example, what is the block size? 16 words are there. So for this 4 bits required. Log of 16 is 4 only. Next one, please understand. Block offset. B1 is block offset. Gives a block number. Please understand. Block number from cache memory. Out of those many blocks in cache memory, it will give one block number. Okay, which likely contains addressed word. Okay. So for this field, how many bits required? So that depends on block offset, depends on the number of blocks. So number of blocks are indicated by capital N. So now log of n base 2. Please understand, this will give lot of information, and problem solving, which I highlighted, which will help us to help us in problem solving. Number of bits required for this field depends on the number of blocks. Okay. The last one gives the tag. Tag nothing but it will check whether, please understand, it will define. So please understand, we will define whether please referred block is present or not. Whether a referred block is present or not in cache, or other way you understand. So which block of main memory is currently reside in cache memory. This you understand. Okay. So number of bits required for tag depends on physical address minus these two you can do, or also understand. Okay. How many blocks are mapping into cache memory? How many blocks are mapping in that case? One block. How many blocks? How many main memory blocks are mapping one location? 8. So this this gives log of m. M is number of blocks in main memory divided by n. Okay, base 2. This also understand. In this example, number of blocks in main memory 32. Number of cache blocks are 4. 32 by 4 is 8. Log 8 is 3 bits. So for this 2 bits required. For this 2 plus 4 6, remaining is 3. You understand? This also understand. So I hope you understand this point more clearly. So why this 3 partitions required? I explained you. I said what is the reason. So if you know the block number, if you searched it, but you cannot guarantee the presented block whether belongs to you or not. It's not guaranteed, because there are many blocks are mapping into that location. There is a confusion. That is the extra information required. That's tag information required. That's the reason physical address is divided into 3 parts. Leftmost 3 bits are used to identify which block is present. Next 2 bits are indicated to search the block number. Next to 4 block indicate the finding the word within a block here. So let us understand. This is a little more clear. Look, all of you. Let me take this. Okay, this one. Okay. Look, the same example I am considering. Look here. So I'll remove this one. Okay. Look clearly, all of you. Currently, these are the blocks are there. Okay. Okay, this is fine. Let it be. Okay. Look, all of you. Look here. So what I said you. So the block number information not sufficient. Extra required. Now please understand. Every block. Let me remove this part and we'll redraw. So every cache block is associated with the tag bits. Every cache block is associated with the tag bits. Fine. So look this now, all of you. Please understand the things here. Okay. Now see. How many tag bits required in this example? 3 bits, right? 3 bits required. How 3 bits required? Out of 32, 8 blocks are mapping here. Suppose now if there are 8 blocks are mapping now, this 8 blocks. How addresses I can write for this? How addresses I can write? Let's see. This is the 0th position. This is position number 1 because 8 are referring, right? So 0, 1. This is 2. This is 3. This is 4, 5, 6, 7 like this. Okay, 7. Like this, 0, 1, 2, 3, 7, 0, 1, 2, 3, 4, 5, 7, 0, 1, 2, 3, 4, 5, 7. Right, understand. Now, how tag bits I am updating here? Whenever, please understand, whenever you are loading a block from main memory to cache memory, so that tag bits you need to update. 8th is the position, 0, 1, 2, 0, 1, 2. Second block it is from this Total 8 block referring, 8 is a second position, 8 1 is second position. So second outright 0 1 0 like this, 5. So 0 1, so 0 0 1 is the 1, this is position. 10, so 0 1 2, so 0 1 0. 15, 0 1 2 3, so 0 1 1 like this, understand. The moment you load the block from main memory to cache memory, immediately tag bits you have to update. How to update the tag bits? How many blocks are referring, and this is the position of that list. 15, 0th, 1, 2, 3, third position. That's what 3 I written. So I hope you understand what I was trying to say. See, tag bits, block offset, word offset. Now we'll see how searching will happen. How searching will happen, we'll observe clearly, ma'am. So now I said, addresses divided into 3 parts. Now every cache block is associated with tag bits, ma'am. Let me write here is a tag, tag bits, okay, tag bits. So indicating this will show whether my block is present or not. How it will show, we'll understand clearly. Now we'll see. Now I'm writing, whenever any reference comes from CPU, please understand the reference, logical address. So this we are converting into physical address, right? With help of what? Memory management unit, right? Yes or no? The physical address. In our example, physical address is what? 9 bits, right? 9 bits, please understand. So this 9 bits I am going to take into cache memory, right? This is a cache memory, okay? Now here is a main memory. If miss occur, I will go to main memory. Otherwise, I will search in from cache only. So this physical address 9 bits you have to split into 3 parts, okay? This is a tag, right? Then block offset, this is a word offset, right? In our example, word offset, how many bits required? 4 bits. This is for 2 bits. This is for 3 bits. Clear, right? Okay. Now step number 1, please understand. Step number 1, take, okay, take block offset bits, please. Take block offset bit. Let's say, so this is 0 1 1 0 1 1 combination, right? 0 0 0 0 0 0 1 like this combination is there, like say. So the block offset given 0 1, assume that 0 1. What is 0 1? 0 1 is 1 block, okay. Step number 1, take a block offset bits, okay. Take a block offset bits. Search block number. So search block number, ma. Search block number, okay, block number. That is what? 1 only, right? So 0 1 nothing but 0 1 nothing but. So this is 0 block, this is 1, this is 2, this is 3. 0 1 nothing but this block only, this block only. I searched, okay. I'll use some combination circuit, I'll search it as well. Search. Then step number 2, please understand. Okay, compare, please understand, compare tag bits. So tag bits of, so 0 1 to block, 0 1 to block. Are you getting my point? Compare tag bits of 0 1 to block means 0 1 means what? 0 1. Where is 0 1? 0 1, this one. Compare this tag bits on 0 0 1, this tag bits to with. Compare tag bits of the 0 1 to block with, please understand, with tag bits of, so tag bits of, so tag bits of physical address. So physical address we got, no, that's split into 3 parts, right? So this physical address tag bits you have to compare, okay. Third step, please see. Third step, if both are same, means if it is compare, both are matched, if both are matched, okay, then what to say? If both are matched, you can declare, right? That is available. If both are matched, please understand, if both are matched, so declare. So that is it. It means what? What does it means? Block is present. So it means a block is present. Then what to do? Step number 4. Okay. So the block is there, right? Then what to do? You have to access. So like no, through what? Word offset. So we can access the word within the block. Within the block. I hope you understand. So if it is not match occur, so you can declare that. So if match is not occur, but declare that the block is not present. This need to be done. So let's work out with the example. All of please understand. Okay. Suppose I am taking the scenario. All of please understand. All of see and understand. So process this is A is running in CPU. Please understand, is running in CPU. It generate the logical address. Please understand something that I translate into physical address. So with help of memory management unit. So this address is for in terms of word number 162 word number required. Decimal I written decimal. Word number how many words are there in main memory? 512 words are there. Suppose generate the address for 162. Okay. So this address comes in a decimal binary form. How to write 162 ma? So 162 means 128 position. Then 64 should be 0, 32 1. So 128 plus 32. So this is 0, 1. This will be 4. So 160. So 160, 2 you need to add. So this 128, 64, 32, 32, 16, 8, 4, 2, 1. Right? This is binary. How many bits? 1, 2, 3, 4, 5, 6, 7, 8. But 9-bit address, right? I am adding 0. So this address came from here, physical address. So now you have to take this physical address. Please, physical address. What is physical address? 0, 1, 0, 1. How many 0? 3 zeros. 3 zeros, 1 0. Oh, right. So this physical address, okay, 9-bit address comes from CPU, right? 9-bit address we got. 9-bit address we got. Fine. So divide into 3 parts: word offset, block offset, tag. Word offset required 4 bits. 1, 2, 3, 4 bits. 4 bits. This is what? Word offset. So block offset required what? 2 bits. Block offset. Remaining what? Tag. Okay. What is step number 1? I said you take the block offset. What is the block offset value? 1 0. It is given 1 0. 1 0 nothing but block number 2 only, right? So in decimal, block number 2. Okay. Block number 2. What is second step? You have to compare, you know. What is the comparison? Tag bits. So tag bits of block number 2, you have to equal to, you have to compare what? Tag bits of physical address. Okay. So you go and see the block number 2, what tag bits are there? Block number 0, 1, 2. Tag bits are 0, 1, 0. So 0, 1, 0. This tag bits are 0, 1, 0 binary. Okay, 0, 1, 0 binary. Now here is tag bits are 0, 1, 0, right? 0, 1, 0. Yes. So both are same or not? Yes, matched or not? Yes, matched. So matched, this match. Then you can declare that. So word number 162, this block is present in the cache memory or not? Yes, it is in cache memory. It is in cache memory. Then what to do? Offset value, take word number, go to this block inside. What is the offset value? 0, 0, 1, 0. Word number 2 required. Take word number 2, place in data bus, that will travel and given to the processor. This way it will happen. Are you getting my point? So now what you can try, take another address, write a 9-bit address, split into 3 parts: tag, word offset, block offset. So first of all, step number 1, take the block offset, search the block number, search, right? In the block number, concerned tag bits you take, compare with the physical address tag bits. If both are matched, okay. If both are not matched, declare the cache miss. What is the solution if the cache miss occur? Take same physical address as it is, go to main memory, split into block number offset. You take the block number, map, apply function k modulo n, place into cache memory, update the tag bits, restart the instruction. Next time definitely that word will be available. I hope it is clear. I hope it is clear. So now just I am making conclusion, because the remaining part I want to take into another session. What I discussed, we understand what is the cache memory, the importance of the cache memory, and what cache memory maintains. Locality of reference can be temporal and spatial locality. Then later I started discussing the cache designing approach into what falls. First component is you have to memory organization, cache address mappings. So from cache address mapping, so there are 3 approaches are there: direct address mapping, set associative, and so like full associative and set associative. Clear? So now direct address mapping we observed with example implementation. Now in the next session I am telling you hardware approach. I am going to give the hardware structure, the searching the things here. No, I have shown the theoretical point how searching happens. How this is going to be implemented by using the hardware component we will observe into next session. So till that time, please, so those who are not watched the videos for like fundamentals of the computer organization which I have taken, I've taken floating point, I've taken memory hierarchy, main memory. So please you can cover, definitely is going to be benefited for you, ma. Okay. So thank you so much all of you.